how it fractures, how the specimen fractures, and from the perspective of the atomic atoms. So look at this picture. I'm going to show you guys, okay? And look at this picture. And so here is the one atom. This is another atom. So this is nuclei. This is nuclei. This is two nuclei, and we have between these two nuclei, the distance is x0, and the distance is called equilibrium and spacing. So A and B, this is x0. So the bond energy, there is a concept which is called bond energy. Bond energy, EB, is the integration from this equilibrium spacing x0 and to the infinity, and the P dx. And P is the force, applied force, right? So P equals, look at here, and P equals dE, the derivative of E with respect to x. So here, this is for, look at this picture, this is potential energy, right? Repulsion, attraction, and when these two guys is too close, repulsion becomes bigger. When these two guys is are staying apart from each other, and there will be some attraction. Okay, so this is the force. When these two guys closer than x0, repulsion. There's a repulsion. When this distance between these two nuclei is greater than x0, and there will have some the attraction. So here is the tension and this compression, this applied force. So here is, this is applied force. And so look at this one. This one is called a cohesive force. So theoretical cohesive strength, and we are going to talk about this theoretical cohesive strength. Which is a property of the material. Different materials have different. This is a theoretical cohesive strength. So sigma C is defined as a PC, which is called cohesive force, and divided by this spacing equilibrium spacing x0 square. So this PC equals EX0 lambda pi and multiplied by 1 over x0 square. So we just plug in this PC into this equation. We can get this sigma C equals E lambda and pi x0. So lambda is a value. Okay, so this here, look at this lambda. So this is lambda. Lambda is about twice of this is the spacing, this is equilibrium spacing. So we can have, this is equation, we call this equation 1. Sigma C is defined as the product of E and this lambda divided by pi multiplied by x0, which is the equilibrium spacing. So this is based on this lambda pi equals sigma C divided by E and x0, right? So you can see that based on this, we can see that sigma C has the same magnitude as that of Young's modulus. Lambda and x0, they have the same these dimensions. Pi is a constant, so sigma C has the same magnitude as the Young's modulus. So here, so this P, the force, can be written as this PC. PC is amplitude, which is a cohesive force of this is approximately the sine function, sine pi x lambda. Right? So if this x is much less than 1, suppose this x is very small, and we know that sine, if the sine x, if x is very small, sine x is almost approximately equal to the x. So this one, if x is very small, and so this pi x, sine pi x equals sine pi x over lambda equals pi x over lambda. So we have this. And then we have, this is a k. this is a stiffness K. K is a P divided by, and this is X, which equals PC multiplied by pi over this lambda. Okay, guys, so this is from the atomic view. Regarding this is gamma S, the gamma S is the surface energy per unit area. So this gamma energy, this is the gamma surface energy, and can be obtained by using this equation. And from 0 to lambda, right? This is from zero to lambda. This is a PC sine pi x lambda x0 squared dx. So this is 1/2, and this is we just plug in PC, right? PC. This is the PCs here, right? This is a PC can be denoted as sigma c multiplied by x0 and square. So PC divided by x0 squared. So this is sigma c sine pi x lambda dx, and here it shows how we get this is the integration of this integrand, and from this 0 to lambda, and so we have this. So you guys just take a look at this is integration, right? And from say this one, where's my mouse? Okay, let me use my mouse. So here, this is how we get this integration. This integration equals 2 multiplied by lambda pi, and we just plug in, and we will have gamma s equals, and this is sigma c. We just take out sigma c. This 2 cancels these 2 lambda pi, and we call this one as this gamma s. Right? Gamma s. We must substitute equation 1 to equation 2, and we can get this sigma c, and which can be written as E gamma s and divided by x0. So this is a very, very important equation. Then we talk about actually, and we know that the actual strength is much larger, much smaller than the sigma c. And sigma c is this is a theoretical cohesive strength. Theoretical cohesive strength is called theoretical. It is very, very huge. It has the magnitude of Young's modulus. However, sigma c, sigma c is not practically. Sigma c is not as large as we expected. Why? Because for any practical specimens, there are a lot of defects, okay? A lot of voids, flaws, defects. So as a result, and we will have strength concentration. And so this is proposed by Professor Iglis. Right? Look at this picture, and look at this picture. And suppose we have, this is the central, this is a crack. This is a central hole. This is a elliptical hole. So this is a 2A and this is a 2B. So at this point A, right? Suppose we have, this is a remote stress sigma. This is the tape, crack tape A. We know that this is sigma A equals sigma multiplied by 1 plus 2A divided by B, right? If this is A is increasing, and so if suppose this A is very, very large, is much larger than this B, and so we will have a sharp crack. And sharp crack means that this crack, the distance between these two crack surfaces is very, very small. It's sharp crack. Sigma A, okay, this is the sigma A at this point A, the crack tape. And given this is nominal sigma, and sigma A divided by this is ratio of sigma A and to sigma, and we call this ratio as the stress concentration factor, right? So this is rho, and rho is radius of curvature, and rho equals B squared and divided by A. And sigma A equal, we can just plug in B, right? With B, and we have B here, right? So B equals square root A multiplied by rho. We just plug in, we can get this, rewrite this sigma A in terms of A and this rho. So we assume sigma A equals, this is sigma C. We see this theoretical cohesive strength. And let's see what will happen. Sigma A equals, assume this A is much larger than B, okay? So this is, and this value will be much larger than this one. So this one can be ignored. So sigma A can be approximated by sigma and this value, because this value is much larger than 1. Okay, so 2 and square root A over rho. So this one, if we let this sigma A equals sigma C, and say sigma C is obtained already, which equals this equation and square root E gamma S x0, right? And so, and we can see that. So this is the, we can sigma A equals this one, right? This is sigma, okay? This is sigma A equals this, and this we can see at what condition, and when sigma, this value, nominal value sigma equals what value, and so this one, and is going to, this specimen is going to fill, the crack initiates. And this is sigma F. We compare Z, we take care of this part and this part, and sigma F, this is which is called microscopic failure strength, and sigma F multiplied by this and equals this. So we can just rearrange this equation, and we can get sigma F E gamma S. So this is and square root and A rho. So you should know that this is in the absence of plastic deformation, the minimum radius a crack tip can have is on order of atomic radius. Rho is around x0, and so rho is around x0. So we can have this sigma F. This is our this is we use this observation. Okay, so rho, when rho, if we do not take care of the plastic deformation, the rho is in the order of, this is the equilibrium spacing and x0. So that's the reason we can write this sigma F equals square root E gamma S, and this is EA. So this is our equation, and this is called microscopic and failure stress. Okay? Any questions so far? So you should know that some students might ask, where is x0? I say this is our observance, and rho is very near x0. So rho, we can treat it as rho equals 0. So this is rho and x0, and they cancel each other. So as a result, we can have sigma F equals square root E gamma S divided by 4A. So this is a microscopic failure strength. So now you should know, and theoretical cohesive strength is on the order of Young's modulus. They have the same order of magnitude as Young's modulus, but usually our this is stress is not, the strength is not very high. Why? Why? Because the defects, the cracks, small cracks, and small voids in the material. So here is the example. This English, and this Professor English give us the theoretical derivation, how to calculate this sigma F. And you can see this sigma F is lower than the sigma C. right? Because A is much larger than this x0. Questions? Okay. If no question, we talk about this is and also the Gachlin and Kaninen and propose this sigma f equals this is alpha square root e gamma s, and this is a, okay, this is crack length. This alpha is very near the 1.0 on the order of unit, and so this is Gachlin and Kaninen proposed very, very similar one. So you can compare this one, and they are very, very similar. Then we talk about, this is the chapter 2.3, the Graves energy balance. This professor and Graves and give us propose this is energy method and in 1920s, okay? And what it says is that this is energy balance says that the total energy equals the potential energy and plus the work required to create new surfaces. Right? Suppose we have a component and there's a crack, or there's no crack. If you want to crack the body, you must apply the force or any kind of external load, right? To provide energy. This energy, when this energy is higher than some threshold value, some point or points, will start, will have crack initiation and then crack propagation. So from the perspective of energy, and we, the Professor Graves give us this equation, and total energy equals potential energy equals work required to create a new surfaces, WS. So this potential energy and supplied by the internal strain energy, okay, because of deformation, and also this is these external forces or other external loads. At the critical point, a critical point means that the crack initiates or the crack propagates. And so this is dE. We take a derivative of E with respect to the crack surface A. So let this guy equals 0, and we have d pi dA and plus d gamma s dA, dWs dA. And we know that, so this is the pi, the potential energy of the uncracked, of the cracked body equals potential energy of uncracked plate, the minus, this is pi sigma a square b, and this is E. So this is B is the thickness of the plate. And so this is pi can be written in terms of pi 0 and also sigma square a square and B, and also the Young's modulus E. And we know that A is a crack surface, or crack surface is equals 2A multiplied by B. It's a 2A, right? 2A multiplied by B is a crack surface. We assume it is a sharp crack. So pi equals pi 0 minus sigma square A square B divided by E. I'm sorry, this is a pi here. We should have a pi here. So d pi dA. So pi 0 is a potential energy of uncracked plate. So this guy d pi 0 dA will be equal to 0. So we have d pi sigma square A and Young's modulus. So because A and B equals this is A, okay, which this take the derivative with respect to A. So we have this equation. And then we let dE dA equals 0. And then we have d pi plus dA and dWs dA, and this guy equals 0 also. So with this d pi dA and d pi dA, we just copy this d pi dA here. And so this dW dA equals 0. Okay, so we should know that the WS Ws equals 2A gamma S. And this is A is a crack surface. We always have two crack surfaces. Do you guys agree? One is up, one is lower. One is up, one is lower. And so this is gamma S is surface energy of the material. Surface energy of the material. So it's a per square. This is a unit square. Per unit area. This is 2A gamma S. Right? So we just plug in and minus pi sigma square A E and plus this is C D omega S and dA with respect to A equals 2 gamma S equals 0. And then, so we have this. This is as this is a critical point. Okay, sigma as sigma F equals sigma F equals this 2 E gamma S divided by pi A and square. So this is equation 2.19. Any questions so far? And so we can write this sigma F as this alpha square root E gamma S, this is A, okay? And we can see very clearly that, and this A, square root A, we can just rearrange this equation a little bit and put this square root A to the left-hand side, sigma F multiplied by square A equals alpha square root E gamma S. And E gamma S is the toughness of the material, right? And sigma square root A is the stress intensity factor K. And we can see that, right? Okay, we can see this is this verifies and the claim that for the linear elastic material and the stress intensity factor approach is equivalent to this is energy approach. So one thing I want to mention is that there's a crack area. So this crack area equals the projected area of the crack, projective area of the crack. So surface area and the crack area, they are different. And surface area 2 multiplied by crack area. Why? Because any crack and will have 2 crack surfaces. So this is the 2 crack surfaces, they are matching surfaces. And you should know this, crack area is the projected area of the crack, right? And surface area is double the crack area. Any questions so far? Okay, and so this Grace approach and can be applied to other crack shape. To this is our other crack shape. For example, for this penny-shaped flaw. For penny-shaped flaw, so this is sigma. Okay, so this is sigma. This is a 3D specimen. Here is a penny-shaped flaw. This is a circle. The crack surface is a full circle, right? So full circle, and the radius is equal to A. So sigma F equals square root pi E gamma S 2 and parentheses 1 minus a nu square A. And nu is a Poisson ratio, and A is a crack, the radius, as shown in this diagram. Okay, so this is the sigma F and how to calculate the sigma F. So up to now, and we only take care of this is the elasticity. So the plasticity has not been involved, right? So, and here this is we are going to talk about modified Graves equation. So Professor Irwin and this is Orwan, and these 2 professors, they independently modified Graves this is expression to account for materials that are capable of plastic flow, and they get the same equation. Okay, so just like the Sir Isaac Newton and the Professor Leibniz, and these two talented guys get the same the equations independently. They do not copy each other. Okay, so this is say Irwin and Orwin. They independently modify the Graves expression and get this equation. What this equation say? Say sigma. This equation says that sigma f, the failure stress equals and square root and 2e is gamma s plus gamma p divided by pi a. So this gamma p comes into play. Gamma p is the plastic work per unit area of surface created, and it is much larger than this is a gamma s. Gamma s is only for elasticity. So this is very, very important one. So this one, so gamma p, so this is sigma f. Okay, you can see this sigma this one can be written as this 2e wf pi a square. This wf is a fracture energy, and which could include plastic, viscoplastic, and viscoelastic and viscoplastic effects. So this equation wf is more general. Okay, so let's look at these three and case scenarios. And for the first case scenario, look at this one. This is ideally this is elastic. This is ideally brittle material. Brittle material, only elastic, no plastic. And this is a crack, and this is a crack, okay? Because this is a crack. It's breaks, see the bond breaks, and this is broken the bonds, right? So for this case, this WF, this is a fracture energy WF equals the gamma S only because no plasticity is involved. So this is case scenario 1. For the case scenario 2, and we have some plastic deformation. This is a crack. This is a crack. And we have some plastic deformation. This WF equals gamma S plus this gamma P. And so this is and so this one is this, right? So, and the third case scenario is this. So this is the brittle material with crack, medium, and this branching. So it is medium and branching. So this one WF equals gamma S divided multiplied by true area and divided by projected area. This true area is this way. You can just this actual area, but the true projected area you just project from here to here. You project in this direction. So this one, this picture gives us the 3 case scenarios. Okay, so this one can accommodate all of these 3 case scenarios. Any questions so far? Okay, no questions. Okay, I want to summarize on what I just talked about today. And first, we take a look at this is the theoretical cohesive strength in the atomic view. And we know that this is a sigma theoretical cohesive strength is on the order of the Young's modulus, which is one is bigger, which is very big, very huge. However, the practical, this is the strength of material can never be that high. What is the reason? The reason Professor Inglis and proposed this is a stress concentration model to account for this is lower actual strength when compared with this is a theoretical strength, and this is Professor Inglis because of stress concentration. Okay, and we know that this is sigma f. The equation how to calculate the sigma f if we know Young's modulus. This is a surface This is gamma S, and this is A. And we also know that the Gibbs energy balance equation, given this is from the energy perspective, and how to derive, this is a sigma F. So you should know this is a derivation. You should know this process. I would suggest you guys to do this is the derivation by yourself using your own hands. And if you have any questions, please come to see me. This gamma S is the surface energy of the material per unit area. And then I pointed out the difference between the crack area and this is the surface area. And the crack, how they are different. And the crack area is a projected area of the crack, and surface area is double. Why? Because for each crack, we have two matching crack surfaces. So both of them will count. This is called surface area. So we have three case scenarios, right? And one is the brittle material, the elastic state only. And the second one is we have elastic deformation and also plastic deformation. And the third one, we have this crack medium and this branching. And for these three cases, and we use one equation to accommodate all these three cases and to calculate the failure, the strength for this material. I want you guys to know this, what these three case scenarios are. Yeah, so this is pretty much what we are going to talk today and for our third lecture. If you have any questions, and we can talk. Yes. So I would like to, I would suggest that you guys look at these lecture notes very closely and be very careful, pay attention to the derivations. If you have any questions, come to see me. Okay, guys? So I would like to conclude today's lecture, and thank you very much, and hope you have a nice evening. Bye-bye.